So we started at least reading the, we'll keep going with the second exercise of the tutorial. So basically we have this a spin prepared in this state. The explicit expression is given there. And then there's a weak measurement of sigma z here. And finally, we measure sigma x, make a projective measurement, and post-select in the final state plus x once we make the final projective measurement. So the first question was to compute the weak value. And then look a little bit at the behavior when I change the initial state. So actually, I could also have done the converse, that is, pre-select plus x, and then make a final measurement of some other spin. So basically, the idea is to see how this weak value changes. And the second question was to solve this problem, well, exactly. So the problem of a spin interacting with a pointer and then strongly measured. So let's look at the solution. So basically, just write the definition. You just compute the weak value. This is quite straightforward. So since we saw last time, yesterday, that we have to treat differently the real part that really gives you some information on the observable you're weakly measuring, and the imaginary part, which is something else. What we do here is, at the end, is just parse the real and imaginary parts separately. That's why it takes this form. Louder. So, okay, so this, we're through copying this. Okay, so now the question is what happens to the pointer, and the pointer will move according to the real part of the weak value. And so what happens when theta is equal to pi over 2? What happens to the real value? Well, of course, it vanishes, right? So you have your pointer here. This is the original, let's say, initial state. Usually there will be some change ruled by the real part of the weak value. But for theta equals pi over 2, there will be a null. You will obtain a vanishing weak value. The result will be 0. And so then the question is, how do you want to interpret this? From an operational point of view, if you have a pointer coupled to the system and nothing happens to the pointer, it's I mean, it's pretty straightforward. It's that the pointer has not seen the observable that has coupled to it. And so basically it means that the pointer does not see the sigma z component. And this is just a consequence of the quantum correlations between post-selection and the quantum correlations that comes from entanglement, and that appears between the system and the post-selected state and the state of the pointer. The pointer just remains in the same state. So the question you can think about is, does that mean that actually the spin component is just not there? Because the pointer is measuring it, it doesn't see anything, right? So we will talk about this point a little bit later today. And so now we can try to work on the second point. Plus x, yes. Yes. And the reason is that if sigma z acts on the plus x state, the transition, so actually it's a spin flip. It goes from plus x to minus x, and so the transition from minus x to plus x cannot happen. So basically, it's very much like we saw yesterday, you cannot reach plus x if sigma z acts on plus x. So that's why it doesn't see the plus x spin, because since we have post-selection at the end, then the correlations impose that the weak pointer state cannot change. Otherwise, we would not have reached the final state. And there's also the question on the behavior as phi tends towards pi. So this, I just have plotted the real part of the weak value. And so basically what you can see is, this is as a function of theta. So what you see is that there's for most of the values of theta, you are actually beyond the eigenvalue. So you have the weak value of sigma z, which is larger than the eigenvalue. So again, as we saw yesterday, this is pretty much expected because of what you're doing. You're recovering the same expectation value, but with different probabilities. So then the outcomes also need to be modified. So now if we want to write the exact wave function, so we have the spin part. This is now the spin part. This is now the pointer. So after the interaction, so this is the interaction Hamiltonian and the evolution generated by the interaction. So in principle, because some people asked, in principle, that you would be able to have the slides. I don't know how, but this has to be worked out. But there's a way in which you will be able to have the slides. So just here you have the interaction. This is we already stated the problem. We just gave you the form of the states. So now this is pretty straightforward to apply sigma z to this spin state. We just write it down. So up to here, you have the evolution of the entangled spin and pointer system. So when you make the post-selection, we are here. And now we explicitly write the action of Q on the pointer. So basically, since the interaction involves Q as a dynamical variable, we would have the pointer in a well-defined state of its momentum. So this is why I'm projecting the momentum. This is the momentum of the pointer. I'm projecting here. And so this gives you, if you assuming, so this is not written here, but we assume that initially we had phi with 0 momentum, then we just have translations. So this gives you plus alpha q and minus alpha q. Now you have the explicit entangled form for your state and pointer state. So up to now we just solved, we just applied the interaction Hamiltonian, the evolution, and we just have this exact, of course, exact given the simplified assumptions I use. And I haven't done anything weak up to now. So the only thing I need to do to assume weakness is to assume that this alpha parameter is small. So as you remember, alpha was somehow the indicator of the strength of the interaction, of the coupling. And if I do this, I just expand to first order my pointer wave functions, as in here. Rearrange, and this is what you obtain. I'm just expanding to first order. I'm not doing anything sophisticated. And then once you rearrange, you employ the usual trick of factoring this out. You see that the weak value actually appears, right? That we have computed in the previous problem. So basically, well, I could do the same thing with the imaginary part, but I'm just interested in the real part. Basically, what you see is that just expanding alpha to first order and rearranging, you see that your pointer wave function is just shifted by the weak value, which is, of course, what we would expect. But here we can explicitly solve the problem and see it happen. Yes. Yes. What is it good for, you mean? Or what's the meaning? So basically, you do a weak measurement because you want, so the question I remember, the original question I was asking is what can I say about the value of some observable between some initial state and some final state, right? So, it's not possible to define, according to standard quantum mechanics, the value of some observable, because if you make a projective measurement, which will give you an eigenvalue in that case, you cannot reach the final state. And so the idea was to generalize the concept of eigenvalue to this situation in which you try to say something about the value of that observable, but without making a projective measurement. So this, I will talk about this a little bit later, but the eigenvalue is associated to an eigenstate, which means, as we saw earlier, that there is a very big change, a huge perturbation in this original state of the system. And here, the weak value, the weak measurement doesn't change the state of the system. Right? So you cannot get an eigenvalue. But you cannot define something different. I mean, you cannot define, you cannot, obtain an eigenvalue here. It would make, such thing doesn't exist. So we're trying to generalize, so the weak value, if you take as the initial or final state an eigenvalue of the measuring of the observable you're weakly measuring, will give you an eigenvalue. And that's the cases in which you're allowed to make a projective measurement, because then you will just project and make the same projection again, so that will change the state of your system. So here we're trying to generalize this idea of eigenvalue to the situations in which you are not allowed to make a projective measurement, but still want to see something about, say something about the value of that observable, about the value of that property. And so the examples we saw, like I think yesterday, was that in this case, for example, we saw that it was pretty consistent, that when we selected, for example, on D1, the weak value was 0 on that range, like 1 here. So again, we just made a weak measurement, and in this case, we saw that the weak value was non-zero on both arms. It was 1/2 here and 1/2 here. And that's something that tells us that the particle went through both arms. So that's what basically the weak value here is telling you. If you make a projective measurement, you will find it either here or here, right? That's the difference. And you will never reach D1 or D2. So we're really trying to try to say something about the position of the particle when D1 has clicked, right? That's the main goal. Okay, so now we'll see the last exercise, last tutorial on computational weak values. Since you seem to like the 3-box paradox, so there's an exercise on this. So again, so these are exactly the same initial and final states that we saw yesterday with the 3 boxes. Remember, we had all these 3 boxes here. So initial state, final state, and we want to open box A by making a strong measurement. That's the first question. And we want to compute the probability of finding the particle in box A. So this is the projector, and now we have eigenvalues, well, 1 and 0 of the projector. So we want to compute the probability of finding the particle in box A, conditioned on the fact that a subsequent strong measurement will bring the system to the state psi A. So we start from state psi I. We make a strong measurement here, and then we will make another strong measurement, and we only are interested in the cases in which the strong measurement leaves us in state psi A. And then, so we want to compute that probability and then compute the probability when we open box B. So what is the probability of finding the particle in box B? So again, I'm making a measurement here, strong measurement here. This, to solve this, we will use the ABL rule we saw yesterday. If you can try to apply the ABL rule to this 3-box problem and see what you can get for PA. So if if I measure pi on the initial state, either I get 1 and left in state A, or I get 0. This is basically what we saw yesterday. If I get 0, then I'm in orthogonal subspace. So if I apply Bayes' rule to compute the probability that A equals +1 condition on the fact that the initial state is psi I and the final state is psi f. So this is just the probability of obtaining psi f when the outcome of the intermediate measurement is +1 times the probability of reaching A from the initial state, and then divided by the sum. So this is the probability of obtaining psi f when I start from psi I and I make any possible measurement. This is why I have a sum here. And of course, the feature, so you will obtain 1, and this is based on the fact that the orthogonal state, that the final state is orthogonal to this. So this is why it will give you 1. So that means that the probability of finding particle in box A condition on the particular initial final states we wrote is 1. You are certain? Yes. I'm taking the complement, but actually if you take BB and CC, it will. Yes? Yes, you're right. Yeah. What do you mean? Yeah, you're right. I think you should take just apply directly on B plus C. But you're right. I think if I do the problem, if you want to obtain 1, you have to use this. You should actually, you're right. I mean, this is, you should use this. He's right. So here I just applied I took the subspace, which gives me exactly the same result. But if you do the things properly, this is what you should take. It doesn't change the result. But, and the same thing here then. You should use AA and CC. So of course the conclusion is that you get, in both cases, a probability 1. So if you open box A, you're sure you will find the particle here. So if you open box A, condition on the printful selection. If you open box B, you're sure to find the particle here. But the crucial point is that, of course, these probabilities are not measured. They are inferred from frequencies you would measure. And the measurements you would do to infer these probabilities cannot be made jointly, right? So there's no contradiction with whatever you could do experimentally. This is just, if you want, a consequence of contextuality. But it's still valuable that standard quantum mechanics, not doing anything special, just tells you that if you make strong predictive measurements with boundary conditions fixed at the beginning and at the end, you get that type of result. So now the second part was to compute the weak values. is something you can do straightforwardly. I don't know if I did this. No. So if I compute the weak values, I'm in the case in which I have this initial state. Then, for example, I imagine I couple the box to some pointer weakly. I reach the final state because this is just a unitary interaction that doesn't perturb much the system. And here I make this final projective measurement, and I obtain some state psi f, which is whatever it is. So that's just psi f. And so what happens to the meter that is coupled here to box A? So here the weak value is 1. So that means that the quantum pointer will have seen a change in its state. Now, if you assume you can, if you could couple a quantum pointer to the complement of A, which is B plus C, then if you do the computation, you would see that the result is 0. What does this mean? Again, I'm coupling. So what I want to do is compare this with the strong measurement case. So here in the weak measurement case, if I couple two pointers, one to A and one to B plus C, I somehow join the boxes and couple the pointer, then each time I find the final system in state psi f, this will be correlated with the fact that the pointer attached, well, interacted with A has moved, indicating that the particle was in the box, but the pointer that was coupled to B plus C has not moved, indicating that there was nothing there. And so, of course, this is to be related to our first result here. We are sure to find the particle in box A. Right? And this is exactly what's happening here. Weak value 0 here means that the meter does not see any particle in B plus C. And so 0. Now, if I compute the weak value of B, so now I am doing something different. Right, I'm coupling a pointer just to box B, only to box B. Then what I will see, since the weak value is 1, is that the pointer sees the particle in box B. And if somehow, well, somehow means in an interferometer type setup, I could do this. I could couple A and C, just A and C. And again, do my pointer thing. Then the pointer here, because the weak value is 0, will not move, so the state will remain in the same state, meaning it does not see the particle in B plus C. And so this is to be related to this result. Basically, that if you look at box B, you are sure to find the particle there. So the last question was the weak value just FC, and this is equal to -1. So you can compute this. And of course, this explains in some sense why this is 0, because you just can add the weak values. 1 and -1 will give you 0. So if you want some, so we will see this. Imagine here you have, instead of boxes, you have paths. So this would be A, this would be B, this would be C. So this would be psi F, psi I. So then your weak value here is 1. Here the weak value is also 1 on this path. On this path, the weak value is -1. But if you just couple a pointer here, the weak value is 0. So the conclusion is that it will not see the particle here. I mean, a pointer coupled to this path at this point will not see the particle. Whereas, so systematically, when you reach psi F, in this setup, you will only see the particle in box A. This is what it means. And of course, the background is quantum interference. And so your particle is not a particle, it's something more sophisticated than a particle. But the difference with the strong measurement is that here we can find the probability 1 if you measure strong in box A, the conditional probability is 1. If you measure box B, the conditional probability is also +1, but you cannot make all these measurements jointly. With weak measurements, we're not perturbing the system, so you can put as many, in principle, weak pointers as you want, and you can obtain all of these results at the same time. So, I would like to say that it's just the way the pointer moves. So some people say it's a negative number. It means there's -1 particle on path in box B. And well, I can give you that answer also. Right? There's -1 particle if you take so if you take a projector to be related the density of the number of particles, then you can say there's -1 particle in box. No, it's not related to the phase. Actually, so I just forget about what I said. There's -1 particle in box C. So it's just, the weak value just gives you the shift of the pointer. And so it's just that there's a shift in one direction here and in the other direction here. And so when you put some apparatus here, both shifts cancel and you see 0. So of course the question is how to interpret this. If the pointer is an indicator of the fact that the particle is there or not, then this means that there's no way you can find a particle here. And this is consistent with the fact that if you had made counterfactually strong measurements there, you can only find the particle in box A, conditioned again on the initial and final state. And this is, of course, a consequence of the fact that particles in quantum mechanics are also waved, and so you have interferences. And this points to the fact that all these interferences are not just the result of some formalism that cannot be related to any physical effect, but that all these interferences do show up in nature. Because you can really couple pointers and see how they move. So the comparison with the strong measurements was to emphasize the fact that it's not totally arbitrary, that it really allows you to obtain the probabilities that you cannot measure jointly in making strong measurements. It's impossible because you're perturbing the system when you make weak measurements. You keep the coherence of the system, you don't disturb the system, but of course you don't obtain eigenvalues because you're not disturbing the system, you obtain something else, and something else is called weak values, and operationally it's how your pointer moves, how the pointer changes its state between the initial one, before and after the interaction with the system. Yes, so this is true in general, so now I don't know if you can say it's resolved, because in some sense it's still there. If you see it's 1, I'm sure to find the particle in box A, because if I join boxes B and C, the meter will not move, but it's also true that I'm sure to find it in B. So this is, so it somehow explains the paradox by the fact that a quantum system has interferences, and so that the interferences just make you see what you see. So in this sense, the paradox is resolved. But on the other hand, somehow you have to explain that if you couple a pointer here, there's a particle, here there's a particle, and here there's none. So that raises the question of what is a particle, of course. A particle can just disappear by, right? So maybe the paradox is gone, but there's still something that is not totally explained. This is what I pictured here. If you have individual pointers in B and C, then you will see that both pointers see the particle but move in opposite directions. So then I have to couple them at some point if I want to make a final projective measurement. So I can do this if you want. But where do I put the weak interaction? Where is my pointer then? You have to tell me where I have to put the weak pointer somewhere. So the final is here, because I make my final projective measurement is here. So then you can have this. You would just have plus 1, and minus 1. Yes, B has 1, yeah, of course. B has 1, A has 1, and C has minus 1. So in this case, you see, but in this case, well, I mean, you don't ask that question here because you're not looking separately at A and B and C. You're just looking at 3 paths, and you don't recombine them. So it's just, you're sure you will find something in 3 cases. If I make a, yes. We'll get sorry. And this, if I make a strong measurement, so here. So the question is, how do I make a measurement in B plus C in this case? That's one measurement. So we're telling I don't understand. Okay, you measure, you have pi A, pi B, pi C. This you can do. And what do you suggest to do? want to write it down? Sorry. This is a valid projective measurement. Yeah, it can be a valid projective measurement.
Wondering what would that do since you're talking about coupling gains.
In the strong case. So then in the strong case, so again, in all these things, I have a definite initial state and a definite final state. This cannot be your state. You have to do something to your state to reach this, right? So you have. When you write your B plus C, actually, you've already done this. This is why I don't understand exactly what you want to do with this. Okay, so here I have this, of course, if you want to find the probabilities. Now what you are measuring is B plus C. Which has to give you 0, because if pi equals 1. Yes. Yes. I'm not sure I really understood what he was talking about, because you're making this thing does not exist. What you can do is this measurement you can do, and then you're in this subspace, but not this thing you cannot do. Yeah, but the cross terms here will not play given the choice of initial and once. Yes. 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 Okay, so you want to make a projection this, yeah, so in this case, we don't have 3 boxes anymore, right? We're going to 12 times. So I would say it's a different problem. Yes, I mean, if you find, you can find any type of observable, and you can try to apply the ABL rule to any observable. That is allowed, but then it's not the same problem. We can think about this later. But still, I mean, if you make B and plus C, you end up with the state B plus C. So it's, this problem, this would be the way to do it. But okay, let's see. Yes. So in which case is it like that? Because we need always to have 3 boxes. We need always a 3-dimensional Hilbert space as a minimum dimension of the Hilbert space. And then you can, of course, make the superposition of 2 of the boxes. But you need a 3-dimensional Hilbert space to begin with. Otherwise, in a 2-dimensional Hilbert space, this cannot work. So it has to be 3 or more, but as in all these contextuality issues, you always need a 3-dimensional Hilbert space, minimum. And then, of course, you do superpositions to so are there any more questions on these? Yes. So the strong measurements, I mean, the problem is that strong measurements are not defined. So you have to assume counterfactualness, and for some people, this is not a problem. For some people, this is a problem. The final one, yes. Here, that leads you here, yes. For projectors, you have to distinguish projectors and other observables. So in general, yes, the weak value gives you a lot more information, and you cannot, even a spin, you cannot have this weak value 0 from strong projective measurements. But for projectors, probably yes, at least the real part of it. The real part of the weak value will relate you to the strong measurements, the probabilities of the strong measurements you could make. Yes, except that in the weak measurement protocol, you end up also doing a strong measurement at the end. So actually, yes, you need this. You need this. Otherwise, you remain in an entangled state, and you can't say anything. So the weak value depends on the final post-selected state. If you look at the, so this in standard quantum mechanics is just a transition amplitude. Right? It's not a probability. And the weak value is actually the ratio of 2 transition amplitudes, one with the interaction and one without. first of all, when we looked at this before talking about the spin, about this, in this example, we saw that the weak value was 0 and 1, or 1/2 and 1/2 if I put the beam splitter. So would you agree that then it is meaningful? Well, this is what this is why in the simple case, you saw that if the post-selection was on D1, the weak value here was 1, and the weak value here was 0. So what this means is that the particle took path 1, actually. That's what it means, because the weak pointer doesn't see anything here. So that's individual. Right. So this, in this case, you're right. The eigenvalues are part of the weak values and the eigenvalues are the same. Now, in the following case, just one, Raphael. So in this case, you have 1/2 and 1/2. So they are different from the eigenvalue, because the eigenvalues, if you make a predictive measurement, is just 1. But they're still meaningful because they tell you that the particle took both paths, right? Now, is it interesting to know that the weak value of a spin 1/2 is 100? So this is, of course, not particularly meaningful, except if you have some specific protocol in which you would couple your pointer to something else. And that would depend on the value of the pointer, and maybe you have a threshold, and maybe, you see? So as such, it may be not very interesting to know that the weak value of a spin 1/2 is 100, but it can play a role. Yes, Raphael? So that's absolutely true, that in typical cases, to say, well, since you have that's what we saw yesterday, since we actually have a very, very small displacement, assuming that the meter state that I'm drawing here has been displaced with a value, you need to repeat the measurements on many copies in order to practice see. I don't know if you see something. I'm just drawing to display that. So this is what for those who didn't see, basically. So if you want to see the difference, and even exaggerating, because actually they're much closer, the difference between the two Gaussians, the one that corresponds to the initial state and the one that corresponds to the final state shifted by the weak value, then you need to repeat the measurement many times. Does that make a conceptual difference? No, not necessarily. You can claim, and some people do, that the weak value is relative to a single system and is not a statistical quantity, even if in order to get it, to observe it, you need to make many more measurements, and you cannot get it in a single shot. But of course, even if you make a strong measurement, a single shot means you have calibrated your measurement apparatus before. I mean, to calibrate the measurement apparatus, you also need many shots. So, I mean, it's true in practice. Conceptually, it's not necessarily true. Some people think the weak value is a statistical quantity, and others don't. And if you look at the relation of this relation, the expectation value given in terms of the eigenvalue here, and the expectation value given in terms of the weak value, you can just say that the weak value is some sort of generalized eigenvalue when the probabilities are those of going from the initial to the final state, which is not an eigenstate of the weakly measured observable. That's true. Yeah, absolutely. That's true, but really no. Yeah, but I agree. I agree with that. But the question is it conceptual or is it practical? Is this a practical necessary difference, or is this does that make a conceptual? I mean, it does not make a conceptual difference. Not necessarily. You can claim that the weak values are statistical, or you can claim they are relative to an individual system. Even though, in order to measure something, you need to make hundreds of measurements. Right? Yes. Yes. So again, the weak value, I always need to make a projection, a predictive measurement at the end. So if at the end, so if you say that the post-selection, the final boundary condition is given, yes, I would agree with that. But actually, it's not, well, I mean, you can also take the point of view that it's not given, that this happens at the end of some forward evolving process. So if it's fixed, if the final boundary condition is fixed, you have to somehow think that something is evolving backward in time. If it's random, if the post-selection is random, then Schrodinger evolution is not enough. You just need the final projective measurement. At the end, yes, we're back to strong measurements, and the weak value of that observable relies on the strong measurement of another observable, the one that measured you. But I think everybody agrees on the fact that in order to see the weak value, you need to make many measurements. We have, so it's not necessary if the weak values, yeah. Well, at least, yes, at least you can defend the point of view that it's only a practical matter and not a conceptual problem. Okay, so we'll move on to the last part. So we're going to see more examples, basically, so which is continuing on this line of thought. We're going to talk about the path of quantum particles, and if I have time, on trajectories, how you can see trajectories with weak measurements. So if we just pause for a second and try to think about the difference between eigenvalue and weak values, then as you know in standard quantum mechanics, well, we say that a given system has a property when the value of that observable is an eigenvalue, and that means that we're an eigenstate of that observable, which is an operator in Hilbert space. So this corresponds to a given subspace of the Hilbert space. As we saw during the first part of the talk yesterday, this means that there was no property before the measurement. And actually what gives you one of the eigenvalues is the fact that the interaction with the pointer drives the state of the system to an entangled state in which each pointer state is coupled with a given eigenstate. And then, of course, we have this famous measurement problem that we talked about yesterday. So at any rate, if you want to reach an eigenstate, you have a strong interaction and so perturbation, and at the end, collapse or reduction, whatever, projected motion. Now, if we just rely on this thing, there are many questions. So we just rely on the eigenstate, eigenvalue link. There are many questions we are not able to answer, which will have meaning. And this is what I tried to convince you about during this lecture is if we want to say something about the particles, about the properties of some particles at some intermediate time, so then we cannot rely on the eigenstate, eigenvalue link. There is this protocol which we described involving weak measurements that tells you something. So what the meaning of what it tells you is controversial, but at least it tells you something. Are able to get a little bit of information on the value of the observable condition on the initial state as we're used to, and also a particular final state that you have to filter to select. So the type of questions that we could answer with weak measurements that have no answer if you only rely on the eigenvalue link. So you are allowed to do that. You can say, in my opinion, only the eigenvalue eigenstate link allows me to define properties of a quantum system, and anything else is not a property, right? And then in that case, first of all, you won't be able to answer these questions, and second, you have to explain what the pointer, weak pointer motions mean, which is what actually most people do. But so what path did the particle take to an initial and a final state? This is what we're going to talk about. Other applications that we won't probably have time to talk about is what can we say about values of non-immediate observables? So the underlying dynamics of an evolving quantum system, I'm going to talk about this in a while, and also the other questions like the time particle spends inside a barrier, so that's another question that has no immediate answer in the standard formalism. So this is very much what I drew before. So we have a three-path interferometer. So it's easy to visualize if you think about spin-1 particles, because in that case, you have a magnetic field here that gives you three different paths according to the azimuthal number, the value of n. But never mind. So you have three paths, and you assume you can recombine them. So this is what Schwinger called the Humpty Dumpty effect. And you make weak measurements at different times, indicated here. And at the end, you make a strong measurement, and you post-select. So here you post-select along this value, this state. So if we want to be specific, we're talking about spin-1 systems. So we start in this state. So this would be the spatial part of the wave function of the state. This would be the spin part. So we can always assume that the spatial part is a Gaussian. And then, so this is the wave function once you are inside the interferometer. You have three paths according to the value of n alpha. So -1, which was the lower path, the middle path 0, and 1, the upper path. And at the end, you choose a post-select on a given state. So basically, we choose a certain direction phi, and a certain, so this is when I make this one measurement here, and a certain state, which would be the m phi equals +1. So this is just to set the the problem. So the thing is, just as in very similar to the three-box problem, I choose the direction phi so that this sum here is 0. sum, when I sum these are just coefficients of which you can compute, but never mind. So I sum the two lower paths, I get 0. Why do I do this? Because then, I'll just jump to this slide. When I do this, this allows me to, so I can compute the weak values, and if this condition here holds, then when I compute the weak values, I realize that the weak value here is 0, and the weak value here is 0. So at t equals 1, I have two weak values at E and F, which are 1 and minus 1. The weak value at 0, at O here is 0, here it's 1, and here again it's plus and minus 1, and here it's 0. So if you want to do the computation explicitly, you have the expression for the weak value. You just apply, start from psi I, you evolve the system from initial time to time 2. Then you make you take your observable here, which is the projector at O, and again, you evolve from T2 to TF, and the final projective measurement, which you could select in this state. So if you apply the evolution operator to the initial state, so you get this on, so D was on the upper path, and then I'm going to time T2, so I'm here. So I got this part here, and then I sum over the two paths because here, here I am. I'm summing the wave packets coming from the k equals 0 and k equals minus 1 paths. And once I do this, then I realize that, okay, so then of course this projecting at O the wave packet at D 0 because there's no spatial overlap between what I see here and here. That's pretty obvious. And my weak value is given then by this expression. And this is why I chose the final preselected state to be 0, because then if like I did here, I chose this to be 0, then my weak value vanishes. This is exactly what I wanted to do, and this is why I chose this final preselected state in order to have this weak value vanish. And so again, this, if you take the, I mean, if you couple a weak pointer here, you will see that, if you couple weakly a pointer here, you will see that it has, it picks up nothing. Here it picks up nothing, but here it picks up something. So one of the ideas of this same type of effect was seen by Weidmann in a nested Mach-Zehnder interferometer. So here you have the normal Mach-Zehnder, and you have a nested Mach-Zehnder inside. And so what he said is that the weak value here is 0. So this is how the Mach-Zehnder is equilibrated. Here it's also 0. But inside the Mach-Zehnder, the weak value of the projectors is not 0. So basically, the contention is that there is, you can find a particle inside, although no particle entered because the weak value is 0, nor exited the inner interferometer. So a possible interpretation of this, if you think that the weakly coupled pointers give you, allow you to reconstruct what is happening in terms of trajectories, is to say that here you have a discontinuous trajectory because you can have a particle here, you can have a particle, you have no particle here, sorry, no particle here, but you have one inside. Which is pretty much what we just saw here for the realization of the three-box paradox. So again, this is a consequence of quantum interference. And if you remember that particles in quantum mechanics are not particles, then this is maybe not very surprising. So what Weidmann said is that you have a trace of the particle inside, but you have no trace outside. And the trace is given by the motion of the pointer, which is 0 inside here and 1, 0 outside, but 1 inside. So now, if in addition to the particle presence, you do the same thing for a particle property, or some other property like its spin, so here I am again using the same type of picture I used here, I used earlier, in which if I have a weakly pointer weakly coupled to the position to the special wave function, then the weak value here will be 1. So I use another notation for weak value. So the value here is 1, the weak value here is 0, which means I really won't see any trace of your special wave function here. You will see 1 here. But if I choose a spin projection, a spin component that is chosen judiciously in a clever way, then I can obtain the opposite effect for weak measurements of that property, which is here the spin along some direction gamma that I just getting at the moment how I choose this. And so basically the image is that a weak pointer here sees the spatial wave function, but does not see, if you, instead of the spatial wave function, you couple the pointer here to the angular momentum, you will see no change in that pointer, and so you will deduce there is no angular momentum there. And the opposite effect you find here. So as we just saw, there's, if you couple the spatial wave function, here the pointer will not see it, it will not change it, it will not move. But if you couple the pointer to the angular momentum of your particle, then there will be a change, which is actually given by the weak value of the angular momentum. So this is, okay, so we can try to look at this in more detail, but this is basically what is called disembodiment, and Aharonov introduced this in a book about 10 years ago, 2005, I think, called this the quantum Cheshire Cat, because the property is seen here, but not the spatial wave function. And here you see the spatial wave function, if you want to find the particle, but you don't see the property. So in this sense, the property is separated from the place where you can find the particle. So this comes out just by computing the weak values. So if you compute the weak value of the projector at point A, that was here. You just apply the formula as you are used to it. You start from the initial state. You have the system evolution up to time t3 where you will make your weak measurement. Here is the projector at point A. Then you keep on evolving from the time of the weak measurement up to the time of full selection. Here you make a strong projected measurement. And you will select on the state that you have conveniently chosen to observe this effect. So if you do this, then just compute the weak value. We'll see the weak value is 1. And if you compute the weak value of the angular momentum, so basically it's exactly the same thing, except that here you put J gamma at pi A, so J gamma at point A instead of pi A. And if you do the computation, you will find that the value is 0. And conversely, if you look here at B plus C, that I also called A bar, then you will see that the weak value is given by this expression, which is exactly the same value you would obtain before entering the interferometer, or that you would obtain at the exit of the interferometer. So the picture it gives you is that the angular momentum would, along that direction, so that component of the angular momentum would somehow travel in this region like this, whereas the spatial wave function would only travel in this region. Although, as we saw earlier, if we make a weak measurement here and here, we are also able to find it. is clear because this is basically why did Aharonov call this a Cheshire Cat? Because, as you remember in Lewis Carroll's novel, you have this cat that gradually disappears, and Alice says that she has often seen a cat without a grin, but a grin without a cat, well, that's pretty curious. Now, if you believe that weak measurements allow you to say something about the grin, which is a property J gamma here, and something about the cat, which would be the fact that you can find or not the particle in some region, then actually you have made some sort of Cheshire Cat. So again, this will rely on how you interpret weak measurements, but at any rate, the motion of the weak pointers, this is something you just get out of standard quantum mechanics, which is the unitary interaction and just final post-selection, so a final projective measurement. And so even if you don't like this interpretation of disembodiment, you still have to account for the fact that a weak pointer here will only change if it's coupled to the angular momentum, and not if it's coupled to the spatial wave function. And here instead, you have the opposite. If you couple the pointer here to the spatial wave function, you will see the particle, you will see the trace of the particle, but you won't see any trace of the momentum. So, what does all this mean? So this is where the controversy lies. The fact that is, I think, undisputed is that by doing so, you open an additional observational window on the evolution of the quantum system. So even if you think that spin component having a value of 100 is not meaningful, well, you can't dispute the fact that you are actually seeing, it's a protocol that allows you to measure experimentally that value. And if you want to say something about the value of the physical property between two measurements, well, this is the best you can do, actually. This is the best you can do. And in the case of null weak values, when the weak value is vanishing, just as in the Cheshire Cat here, the reason this is why we worked out these examples, is that the transition amplitude from your initial, from your initial transition amplitude to your final state is 0. And this is, again, something that is not mysterious. In standard quantum mechanics, if you, I don't know, if you have a transition between radiative transitions that are forbidden, I mean, you don't think of them as being physical. If the transition amplitude is 0, then it means that you cannot have a transition from your initial state to the final state. So I'm just giving some elements. I don't want to impose my own view, so just you can think about the meaning of these weak values. Yes, the last observation is that should play into the interpretation that you can make of this, is that if you abide by the eigenvalue eigenstate link, then you have your observable, you have some eigenstate, some eigenvalue, and there is no ambiguity. Here there's sort of ambiguity, is that you're looking at an observable without changing the quantum state. So the question is, should you ascribe, when you ascribe a property to a quantum system, should you attach this property to the quantum state or to the observable? So, I mean, if you're pragmatic, then you would just look at the pointer, but then you want to understand what the pointer is telling you. So the pointer is moving according to the weak value, but then the quantum state is not changing. Part of the weak measurement protocol, yes. So the final measurement is a measurement of some observable B. And so you project to an eigenstate of the observable B that has some well-defined property. But now the weak measurement is relative to another observable A, right? And so the state is not changed there. We're just looking at A, observable A, and the weak value of observable A. But you're not changing, I mean, when you get this eigenvalue, you are changing the state of the system to an eigenstate of this B. When you're weakly measuring A, you're not doing that. Yes. Absolutely, yes. This is the pointer is being affected when the final projective measurement takes place, because this is what happens when you have an entangled state and if you have Alice and Bob share an entangled state, when Alice makes a projective measurement, then this will change Bob's state. This is exactly what is happening here. When you make the final projective measurement, then you are modifying the pointer state. Yes, because the interaction took place at the time of the interaction took place at some time, which I call TW, and as you remember from the definition I gave it at the beginning, the weak value here can always be written this way. As the initial state evolved forward in time up to the time of interaction, in this final post-selected state evolved backward in time from the final time to the time of interaction. Basically, the weak value really reflects the time, what happened at the time of interaction. Even though, as you marked, the last projective measurement is made at some other time. But the final projective measurement is going backward in time up to TW. So I tend to think that, I mean, I like this. So I tend to think that I mean, we really have an observational window on what's happening when a quantum system evolves. And this tells us that all these interference effects are somehow related to a real physical phenomenon. I mean, it's not just state vector is more than a bookkeeping device in this sense. The state vector is more than a bookkeeping device. All these all this mathematical formalism that we use about the interference and all these things really happens. So that's my lesson for me. No, I wouldn't go that far. But I would say that yeah, well, because I don't know, you weren't here at I don't think we got the first lecture yesterday, but I really started saying that the main problem with quantum theory is that we cannot make any reference between the theoretical terms of the formalism and some aspect of physical reality. So that was the main issue. In classical mechanics, we know that we have some basic ontology in terms of point-like particles. We know that reality is not made of point-like particles, but we know how to relate parts of physical reality to point-like particles. Instead, if I use classical mechanics in terms of canonical transformations and Hamilton-Jacobi equations, then there is the quantum, there is a classical action, and the classical action does not refer to aspects of the physical world, right? It's just an epistemic term within within classical mechanics. So basically, so the main epistemic, because okay, I'm discriminating between. So I have a physical theory, I have theoretical terms in that theory, and I want to know if those theoretical terms refer to some aspect of physical reality. I'm not saying there's a correspondence between each term and physical reality. I want to know. Okay. And so what I'm saying here is that if you look at the motion of material points, then the basic ontology is made of material points. And so those dynamical laws here refer to how the material points move in reality, even though reality is not made of material points. But if I write, I use the formalism derived from Lagrangian and canonical transformations, and I have quantities like classical action that is defined in an abstract configuration space. It does not correspond to something in the physical world. That's what I'm discriminating. And so so what I'm starting from this, because then the question is whether the state vector is more like the action or more like the point-like particles, or is the state vector referring term or not, or just an epistemic term? So I'm not saying the state vector is a referring term in the sense that it refers to a physical reality, but I'm saying that it's not only an epistemic term. Yes, in classical I have no. So I think weak measurements are. So in quantum mechanics, the main problem is that we can't ascribe reference to the state vectors, and we don't know. I mean, the received view, it's just that all these things are computational tools, just operations. And I think weak measurements tend to think that the state vector is more than that. So I wouldn't go so far as saying that it's a referring term, that there's really something out there that is directly related to the state vector. But the fact that we can see all these pointers move according to what the weak value tells you to, what you expect from the weak values, makes you think that it's going upward from something non-referring to something that is referring. So yes, in this sense, I tend to think that it gives you an additional grip on reality that you don't have if you don't just refuse to use it. Well, I don't know. No, I'm very, so basically I criticize people who say they can just come up with some arbitrary ontology without sufficient arguments or sufficient warrants that this ontology is true. Because then it's what I call a supermarket of interpretations, and I'm not happy with that because I think it undermines scientific theory. That's my point. we the real reality is something we don't have access to unless we're God. We're not, I think. So that is pointless. But it's like having some sort of map, and without, of course, being able to go and verify that the map corresponds to the real reality. Now, I'm not interested to know if the real reality has a classical action. Maybe it does, but who knows? I mean, that's an answer. That's a question which has no answer. So I'm not interested in that question because I can't answer that question. But what I want to know if there is something, if there is an action in the physical world. I mean, if there's an object that is the action in the physical world. Is there such thing? No. I mean, at least within classical mechanics, no. The action is just a quantity that is derived, and you understand what it means because you can relate it to the basic ontology. In quantum mechanics, you cannot do that. You don't know what the basic ontology is. Well, you can make, well, I mean, if you want to see the, oh, well, no, I mean, you need observational warrants. You need to do a lot of things. You have to accumulate evidence that it's there. So if you want to look for some classical action, then you should devise experiments and see the classical action, which of course is, as you know, is a quantity that lives in some abstract configuration space and so on. So if you look for the classical action and then you accumulate evidence, you have observational warrants and that kind of thing, then yes, then you can say the classical action would exist like that. Okay, so I think it's maybe time for lunch. Thank you.